Welcome to Basic Mathematic. Arithmetic, sequences, and series. Arithmetic begins with numbers and counting. Numbers are mathematical objects used to count, measure, and labels. 1, 2, 3. 4, 5, 6, 7, 8. 9 and 0 are called digits in mathematics. Today, we learn about sequence in mathematics. A sequence is a set of quantities arranged in a definite order. Natural numbers are an arithmetic sequence. First and basic sequence in mathematics are natural numbers: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and so on. Counting on fingers. It is also in sequence. Unary, the Stone Age number, unary counting method, was working for ages. It was a popular way to keep counting and recording, marking permanent record by engraving it on stone or on metals. Note here its sequence. The sequences, a set of numbers, stated in a definite order, such that each number can be obtained from previous number, according to some rule, is a sequence. Example of sequences. One, 3, 5, 7, 9, 11, 13, and so on. Next example of sequences is 2, 4, 8, 16, 32, 64, and so on. In the example of sequences 1, 3, 5, 7, 9, 11, 13. Note, each number is increasing by 2, so the next number is 13 plus 2 is equal to 15, followed by 17, and so on. In another example of sequences, 2, 4, 8, 16, 32, 64. Note, each number is increasing by a factor of 2. The next number is 64 times 2 is equal to 128, followed by 128 times 2 is equal to 256, and so on. Term. Each number of sequences is called a term. In a sequence, 1, 3, 5, 7, 9, 11, 13. Each number is a term of the sequence. Also for 8, 16, 32, 64 are the terms of another sequence. The infinite sequence. After the last term of a sequence, we can write next term, so this process will continue indefinitely. Such sequences are infinite sequence. Example of infinite sequence of odd numbers: 1, 3, 5, 7, 9, 11, 13, 111, 113, 115, 10,011, 10,013, 10,015, and so on, will continue indefinitely. So it is an infinite sequence. Finite sequence. However, if we restrict our attention to the limited number of terms of a sequence with clearly defined first and last terms of the sequence, then the sequence is a finite sequence. In a 7-term sequence, 1, 3, 5, 7, 9, 11, 13. First term is 1, and last 7th term is 13. So it is finite sequence. In another example of finite sequence of 10-term sequence, 2, 4, 8, 16, 32, and continued to 512, 1024. First term is 2 and last 10th term is 1024. The sequence. We can also define in mathematics. Sequences are the set of numbers written in a particular order. We note sequences of natural numbers: 1, 2, 3, 4, 5, 6. Sequences of odd numbers: 1, 3, 5, 7, 9, 11, 13. Sequences of number multiple of 2, 2, 4, 8, 16, 32, 64. Sequences of differ by increasing numbers, starting from 1 2 increased by 1 followed by 4 increases by 2. Then 7 increases by 3. Then 11 increases by 4. Then 16 increases by 5, and so on. The arithmetic sequence. The characteristic of an arithmetic sequence, whether finite or infinite, is that there is a common difference between two successive terms. In an arithmetic sequences of 1, 3, 5, 7, 9, 11, 13, the common difference is 2. Note, 13 minus 11 is equal to 2. 11 minus 9 is equal to 2. 9 minus 7 is equal to 2. 3 minus 1 is equal to 2. In another arithmetic sequence of 4, 7, 10, 13, 16, the common difference is 3. Note, 7 minus 4 is equal to 3. 10 minus 7 is equal to 3. 13 minus 10 is equal to 3. 16 minus 13 is equal to 3. In an arithmetic sequence, we label or write the first term as A and common difference as D. So we write the second term as A plus D, third term as A plus D or A plus 2 times D, fourth term as A plus 3 times D, fifth term as A plus 4 times D. We write the 15th term as A plus 14 times D. Note the coefficient of D, 14, is 1 less than the term number 15, or as A plus 15 minus 1 times D. So the 20th term ASA plus 19 times D or A plus 20 minus 1 times D, and so on. So we can define a general term, the nth term as A plus n minus 1 times D. Even natural numbers are an arithmetic sequence with a common difference of 2. As first number is 2, second number is 4, third number is 6, 8, 10, 12, 14, and so on. 2. Note even numbers are actually 2 times the natural numbers, so we can write a general even number as 2 times n. Odd natural numbers are an arithmetic sequence with a common difference of 2. As first number is 1, second number is 3, third number is 5, 7, 9, 11, 13, and so on. Comparing with even numbers, odd numbers are actually 1 less than even numbers. So we can write a general odd number as 2n minus 1. In any arithmetic sequence, finite or infinite, the terms of a sequence are generally labeled as U1, U2, U3, U4, with common difference is U4 minus U3 equals D. The nth term of a sequence is labeled as UN. The first term U1 is A. Second term U2 is A plus D. Third term U3 is A plus 2 times D. Nth term UN is A plus n minus 1 times D. We explain and work out with the help of an example for an arithmetic sequence: 3, 7, 11, 15, 19. Find the 20th terms of the sequence. Note: the common difference is U4 minus U3 equals D, or 15 minus 11 is equal to 4. The first term U1 equals A is 3. The 20th term of a sequence is U20. U20 equals A plus 20 minus 1 times D. U20 equals 3 plus 20 minus 1 times 4, or U20 equals 3 plus 19 times 4. U20 equals 3 plus 76 equals 79. Example: an arithmetic sequence has a first term of 120 and 10th term as 57. Find the 15th term. Solutions. To understand the arithmetic sequence better, we first formed the sequence based on our input. First term is it equals 120. 10th term U10 equals 57 equals A plus 10 minus 1 times D, or 57 equals 120 plus 9 times D, or 9 times D equals 57 minus 120 is equal to minus 63, or D equals minus 7. The common difference is minus 7. The arithmetic sequence is 120, 113, 106, 57, 50, 43, 36, 29. First term is A equals 120, and the common difference is minus 7. So the 15th term, U15 equals A plus 15 minus 1 times D, or U15 equals 120 plus 14 times minus 7 equals 120 minus 98 equals 22. Example: an arithmetic sequence has a first 4 terms as 5, x, 13, e. Find the value of x and y. Solutions. Note here: first term is 5 and common difference is D. The third term U3 equals A plus 2D equals 13, or A plus 2D equals 13, or 2D equals 13 minus equals 13 minus 5 is equal to 8, therefore D equals 4. Therefore the sequence is 5, 9, 13, 17, 21. And from the sequence x equals 9 and y equals 17. Example: find the nth term of 20, 17, 14, 11. Note here: first term is 20, and common difference is D. The second term u2 equals a plus d equals 17. Therefore, d equals 17 minus 20 equals minus 3. And nth term un equals a plus n minus 1 times d equals 20 minus 3 times n minus 1 equals 20 minus 3 times n plus 1 equals 23 minus 3 times n. Example. In one arithmetic sequence, the m term um equals n and n term un equals m. Find the common difference. And m plus n term um plus n. Let the first term is a, and the common difference is d. So the m term um equals a plus m minus 1 times d equals marked as equation number 1, and the n term un equals a plus n minus 1 times d equals m marked as equation number 2. We have equation number 1 is a plus m minus 1 d equals n, and equation number 2 is a plus n minus 1 d equals m. After subtracting equation number 1 from equation number 2, we have m minus n equals n minus 1 m plus 1 d, or d equals m minus n by n minus m equals minus 1. So the first term a equals n minus m minus 1 times minus 1, or a equals n plus m minus 1. M plus n term um plus n equals a plus m plus n minus 1 times d, or um plus n, is work out as 0. We now know the numbers. We understand digit. Now learn about an integer. The integers are whole numbers, just like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. An integer could be a positive integer, just like plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7, plus 8, plus 9, plus 10, and so on. And an integer could be a negative integer, like minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8, minus 9, minus 10, and so on. In an arithmetic sequence, if the common difference between two successive terms is negative, the successive terms will be decreasing in such a way that next few terms could be negative. Take, for example, an arithmetic sequence starts from 6 with a common difference of minus 2, 6, 4, 2, 0. Minus 2, minus 4. To understand, let's follow the number line. Explain now. Note the number line shown here. -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. Note 0 is an integer too, and 0 brings continuity from positive integers to negative integers. To understand an arithmetic sequence with positive and negative integer, we solve an example. An arithmetic sequence has -20 as its first term and a common difference is 3. Find its 10th term. Solution. Note here, the first term a is -20, and the common difference d is 3. The 10th term would be u10 equals a plus 9 times d equals 13, or u10 equals -20 plus 9 times 3 equals 7. Therefore, the 10th term equals 7. Another example, an arithmetic sequence has a first 4 terms as 4 minus square root 3, x, y, and 2 square root 3 minus 2. Find the value of x and y. Solution. Note here, the first term is 4 minus square root 3, and the common difference is d. The fourth term would be u4 equals a plus 3 times d, which is given as equals 2 square root 3 minus 2, or 4 minus square root 3 plus 3d equals 2 square root 3 minus 2. Or 3d equals 2 square root 3 minus 2 minus 4 plus square root 3. Therefore, 3 times d equals 3 square root 3 minus 6. Or d equals square root 3 minus 2. Note here, the first term a is 4 minus square root 3 and the common difference is d equals square root 3 minus 2. So the second term, x, equals u2 equals a plus d equals 4 minus square root 3 plus square root 3 minus 2 等于2. And the third term y equals u3 equals a plus 2d equals 4 minus square root 3 plus 2 square root 3 minus 4 equals square root 3. Arithmetic sequences 4 minus square root 3, 2 square root 3, 2 square root 3 minus 2. Sequences and series. Sequences and series. Please don't get mixed up with sequences and series. They are two different mathematical things.
In mathematics, the series is sum of terms of numbers in a sequence.
In mathematics, The series is a sum of number in a sequence.
To generalize, we can say, series is the process of addition of terms, of ordered finite or infinite sequences.
1 plus 2 plus 3 plus 4 is equal to 10. 2 plus 4 plus 6 plus 8 plus 10 plus 30 equals 240.
Two plus 4 plus 6 plus 8 plus 10 plus, on to plus 30 plus and so on. If a sequence is infinite, then the sum is infinite.
For example, sum of all odd number. 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus 15 plus 17 plus 19 plus is infinite. Example of some series. 1 plus 2 plus 3 plus and so on. 1 plus 3 plus 5 plus 7 so on. 2 plus 4 plus 8 so on. 1 plus 2 plus 4 plus 7 plus 11 so on. Let's add numbers of 2 terms. 1 plus 2 is equal to 3. 3 terms. 1 plus 2 plus 3 is equal to 6. 4 terms. 1 plus 2 plus 3 plus 4 is equal to 10. And so on. Can we add quickly? When there are more terms. So we need to develop a method or a formula. Let's add 7 terms of natural numbers sequence from 1 to 7. Therefore, sum of 7 term S7 equals 1, 2, 3, 4, 5, 6, 7 equals 28. To verify and set up a method to total all number, we proceed as follows.
Let we denote S7 as sum of 7 terms. So the sum S7 equals 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. If we write the series in reverse order, the sum will be the same. Therefore S7 equals 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. Let us add above two sums. S7 equals 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. S7 equals 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. Therefore 2 times S7 equals 8 plus 8 plus 8 plus 8 plus 8 plus 8 plus 8 is equal to 56. 2 times S7 equals 7 times 8 equals 56, or S7 equals 28. Note here, the sum of individual terms of two series written above in right and reverse order is same as 8. Now let us try adding 11 terms of numbers from 1 to 11. The sum of 11 terms S11 equals 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11. And add 11 numbers from 11 to 1, in reverse order. S11 equals 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11. S11 in reverse order equals 11 plus 10 plus 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. 2 times S11 equals 12 plus 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 12. 2 times S11 equals 11 times 12 or 132, or the sum S equals 66. Note, sum equals number of term times, first term plus last term, over all divided by 2. Or sum equals 11 times 1 plus 11, divided by 2 equals 66. Let's add 10 terms of sequence starting from 10. 10 plus 15 plus 20 plus 25 plus 30 plus 35 plus 40 plus 45 plus 50 plus 55. Note first term is 10 and last term is 55. Let's add all 10 terms from 10 to 55 twice. First in right order and then in reverse order. S equals 10 plus 15 plus 20 plus 25 plus 30 plus 35 plus 40 plus 45 plus 50 plus 55. S equals 55 plus 50 plus 45 plus 40 plus 35 plus 30 plus 25 plus 20 plus 15 plus 10. 2 times S equals 65 plus 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 65. 2 times S equals 65 times 10 or 650, or S equals 325.
Note, sum equals number of term times, first term plus last term, divided by 2. Or for this case, S equals 10 times 10 plus 55, divided by 2 is equal to 325. Series and sigma. Series is sum of number in a sequence. Sn equals 1 plus 2 plus 3 plus 4 plus till n. Sigma notation is a second notation to denote the sum of terms. It is shown here as Greek letter sigma n.
Greek letter sigma. As a symbol to inform us T. Hat, we are carrying out a summation.
Greek letter sigma stand for the sum of.
The notation sigma for the sum of finite terms is expressed, starting from first term u1 as I equals 1 to nth term un as I equals n. The ui is a general term. Please note how it is written, with letter sigma and the general expression of term ui. Expressing the lower or starting number as I equals 1 to last number I equals n on the top of sigma letter, which is equals u1 plus u2 plus u3 plus un minus 1 plus un. Properties of sigma n. Number 1. Sigma is distributive. That is sigma n plus m equals sigma n plus sigma m. When the sequences have two or more variables u, v in terms. Sigma ui plus 6. From I equals 1 to I equals n is equals u1 plus v1 plus u2 plus v2 plus u3 plus v3 plus un minus 1 plus vn a minus 1 plus un plus vn equals u1 plus u2 plus u3 plus un minus 1 plus un plus v1 plus v2 plus v3 plus vn minus 1 plus vn. Therefore sigma ui from I equals 1 to I equals n plus sigma vi from I equals 1 to I equals n. Properties of sigma n. But note here, sigma is not like a bracket as we used to. That is sigma n times m not equal to sigma n times the sigma m. We can verify it with an example. Sigma n times n from I equals 1 to n equals 1 times 1 plus 2 times 2 plus 3 times 3 plus for the times if a plus 5 times 5 equals 1 plus for plus 9 plus 16 plus 25 equals 55. Sigma n from I equals 1 to I equals 5 equals 1 plus 2 plus 3 plus 4 plus 5 equals 15. So 55 not equal to 15 times a 15. Properties of sigma n. Number 2. Sigma k times ui from I equals 1 to I equals n equals k times sigma ui, where k is constant. The sigma k times ui equals k times u1 plus k times u2 plus k times u3 plus k times un minus 1 plus k times u underscore n equals k times in bracket u1 plus u2 plus u3 plus un minus 1 plus un equals k times sigma ui. Properties of sigma n. Number 3. Sigma k equals n times k. Adding a constant term k, n times. Sigma k from I equals 1 to I equals n equals k plus k plus k plus k plus k plus k. That is equals n times k. Arithmetic series. An arithmetic series of n terms with first term u1 equals a and difference between two successive term d is written as a plus u2 plus u3 plus u4 plus u5 plus un, where second term u2 equals a plus d, third term u3 equals a plus 2 times d, fourth term u4 equals a plus 3 times d, nth term un equals a plus n minus 1 times d. Sigma underscore I equals 1 caret I equals n u underscore I equals n times a plus n minus 1 times d divided by 2. N divided by 2 times 2a plus n minus 1 times d. Sum of n terms equals half n times first term plus last term. We solve some arithmetical sequences problems. Given that ui equals 5 plus 2i and that vi equals 2 minus 5i. Find A. Sigma underscore equals 1 caret equals 5 U. And sigma underscore equals 1 caret equals 5 V. B. Sigma underscore equals 1 caret equals 5 2 UI minus VI. C. Sigma underscore equals 1 caret equals 1000 5 UI plus 2 VI.
Example. Given that UI equals 5 plus 2I and that VI equals 2 minus 5I, find sigma underscore equals 1 caret equals 5U. So, sigma underscore equals 1 caret equals 5 plus 2I equals 5 plus 2 times 1 plus 5 plus 2 times 2 plus 5 plus 2 times 3 plus 5 plus 2 times 4 plus 5 plus 2 times 5 equals 7 plus 9 plus 11 plus 13 plus 15 is equal to 55.
Or first simplifying sigma as per distributive law and solve this. Sigma underscore equals 1 caret equals 5 plus 2I equals sigma underscore equals 1 caret equals 5 plus 2 times sigma underscore equals 1 caret equals 5 I equals 5 by 5 plus 2 times 1 plus 2 plus 3 plus 4 plus 5 equals 25 plus 2 times 15 equals 25 plus 30 equals 55. Example. Given that UI equals 5 plus 2I and that VI equals 2 minus 5I. Find sigma underscore equals 1 caret equals 5 VI. So, sigma underscore equals 1 caret equals 5 2 minus 5I 2 minus 5 by 1 plus 2 minus 5 by 2 plus 2 minus 5 by 3 plus 2 minus 5 by 4 plus 2 minus 5 times 5 is equal to minus 3 minus 8 minus 13 minus 18 minus 23 equals minus 65. Or first simplifying sigma and solve this. Sigma underscore equals 1 caret equals 5 2 minus 5I equals 5 times 2 minus 5 times 15 equals 10 minus 75 equals minus 65. Example. Given that UI equals 5 plus 2I and that VI equals 2 minus 5I. Find sigma underscore equals 1 caret equals 5 2UI minus VI. So, sigma underscore equals 1 caret equals 5 2UI minus VI. Sigma underscore equals 1 caret equals 5 2 times 5 plus 2I minus 2 minus 5I. Or first simplifying the bracket and solve this. Sigma underscore equals 1 caret equals 5 10 plus 4I minus 2 plus 5I equals sigma underscore equals 1 caret equals 5 8 plus 9I equals sigma underscore equals 1 caret equals 5 8 plus sigma underscore equals 1 caret equals 5 9I is equal to 5 times 8 plus 9 times 15 equals 40 plus 1 35 equals 175. Example. Given that UI equals 5 plus 2I and that VI equals 2 minus 5I. Find sigma underscore equals 1 caret equals 1005ui plus 2vi. So, sigma underscore equals 1 caret equals 1005ui plus 2vi equals sigma 5 times 5 plus 2i plus 2 times 2 minus 5i. Or first simplifying the bracket and solve this. Sigma 25 plus 10i plus 4 minus 10i equals sigma underscore equals 1 caret equals 1029 equals 29 times 1000 is equal to 29,000. Example, 30 numbers are in arithmetic sequence. Sum of all numbers is 270 and last number is 38. What is first number? Given here, n equals 30, u 30 equals 38, and sigma underscore equals 1 caret equals 30 equals 270. Let the first number is u1 equals a and last 30th number is u30 equals b. Sigma underscore equals 1 caret equals 30 equals n 2 times a plus b equals 30 halves times a plus 38 equals 270. Or a plus 38 equals 270 divided by 15 is equal to 18. A equals 18 minus 38 equals minus 20. Examples for practice. The solution will follow. Given that ui equals minus 3 plus 4i and that 6 equals 12 minus 3i. Find D. Find the general term un of the AP. Given that sigma underscore equals 1 caret equals ui equals n by 2, 3n minus 1. We solve this problem in same way as we did last time, so you please follow the steps. We solve this problem in same way as we did last time, so you please follow the steps. We solve this problem in same way as we did last time, so you please follow the steps. Here we presume the sum of series involving squares, that is sum of 1 square plus 2 square plus 3 square plus 4 square, etc. Up to 10 it is 385. Next example. Find the general term un of the arithmetic sequences. Given that sigma underscore equals 1 caret equals ui equals n by 2, 3n minus 1. As we know, the sum of the n term equals half n times first term plus last term. Let first term u1 equals 1 and nth term is un equals b. Sigma underscore equals 1 caret equals ui equals n2 u1 plus un. Comparing with given in question. u1 plus un equals 1 plus b equals 3n minus 1. Or b equals 3n minus 2. Or the general term un equals 3n minus 2.
The geometric sequence. Geometric sequence. Note the following sequences: 2, 4, 8, 16, 32. And second sequence: 2, 6, 18, 54, 162. We noticed here that the difference between two successive terms in both the above sequences is not same, but it is gradually increasing. So they are not the arithmetic sequences. As the terms are rapidly increasing, we check the ratio of two successive terms. It is, in first sequence, 4 divided by 2 is equal to 2, or 8 divided by 4 is equal to 2. 16 divided by 8 is equal to 2, or 32 divided by 16 is equal to 2. In second sequence, 6 divided by 2 is equal to 3, or 18 divided by 6 is equal to 3. 54 divided by 18 is equal to 3. 162 divided by 54 is equal to 3. We noticed a pattern. Each term is increased by a constant factor of the previous term. In first sequence this factor is 2, and in second sequence the factor is 3. Please note, in the sequence 2, 4, 8, 16, 32, in which each term is obtained by multiplying the previous one by a fixed quantity or number 2. Such a sequence is known as geometric sequence. The geometric sequence is a sequence in which each term is obtained by multiplying the previous one by a fixed quantity. Note in the sequence 2, 6, 18, 54, 162, in which each term is obtained by multiplying the previous one by a fixed quantity or a factor of 3. Note the sequence 2, 6, 18, 54, 162. It is formed by starting with the first term as 2. Then multiply it by 3 to get second term 6. Again multiply it by 3 to get third term 18. And multiply it by 3 to get fourth term 54, and multiply it by 3 to get fifth term 162, so on. Such sequences are known as geometric sequences. Take another sequence, 222, 0.2, 0.02, is formed by starting with first term as 200. Now, multiply it by 0.1 to get second term 20. Again multiply it by 0.1 to get third term 2. Again multiply it by 0.1 to get fourth term 0.2. Again multiply it by 0.1 to get fifth term 0.02. This sequence is a geometric sequence. The constant multiplier of each successive term in such a sequence is known as the common ratio. The common ratio of the sequence 2, 4, 8, 16, 32 is 2. The common ratio of the sequence 2, 6, 18, 54, 162 is 3. The constant multiplier of each successive term in such a sequence is known as common ratio. The common ratio of the sequence 222, 0.2, 0.02 is 0.1. In geometric sequence, first term is denoted as V1 equals A, and that common ratio as R, the general nth term as Vn. In the sequence 2, 6, 18, 54, 162, the first term as V1 equals A equals 2, and common ratio as R equals 3. The second term, V2 equals A times R equals 2 times 3 equals 6. The third term, V3 equals AR times R equals AR squared, equals 2 times 3 equals 18. The fourth term, V4 equals AR squared times R equals R cubed, equals 2 times 3 equals 54. The fifth term, V5 equals AR cubed times R equals A times R to the power of 4 is calculated as 162. Note R equals V2 divided by V1 equals 6 divided by 2 is equal to 3. R equals 18 divided by 6 is equal to 3. Therefore, R equals Vn divided by Vn1. In the sequence 222, 0.2, 0.02, the first term as V1 equals 200, and common ratio as R equals 0.1. The second term, V2 equals A times R equals 200 times 0.1 is equal to 20. The third term, V3 equals AR, R equals AR squared equals 20 times 0.1 is equal to 2. The fourth term, V4 equals A times R squared times R equals A times R cubed, equals 2 times 0.1 is equal to 0. 2. The fifth term, V5 equals A times R cubed times R equals AR to the power of 4, 等于 0.02. Therefore, the general nth term would be Vn equals A times R to the power of n minus 1. For practice and understanding, let us solve. Find the 10th term in the sequence 2, 6, 18, 54, 162. The first term as V1 equals A equals 2, and common ratio as R equals 6 divided by 2 is equal to 18 divided by 6 is equal to 3. Because the general nth term is Vn equals A times R to the power of n minus 1. Therefore, the 10th term, V10 equals A times R to the power of 10 minus 1 is equal to 2 times 3 to the power of 9 is equal to 2 times 19, 683, equals 39,366. Find the 8th term of the sequence. 1 minus half, 1/4, minus 1/8, 1/16. The first term as V1 equals A equals 1, and common ratio as R equals 1/ divided by minus 1/2, sad face, minus 1/8, divided by 1/4, equals minus half. Because the general nth term is Vn equals A times R to the power of n minus 1. Therefore, the 8th term, V8 equals A times R to the power of 8 minus 1, equals 1 times minus 1/2, to the power of 7 equals minus 1 divided by 128 equals minus 0.00788125. The geometric series.
The geometric series.
The geometric series. When the term of a geometric sequence are added, the result is a geometric series. For example, the sequence 3, 6, 12, 24, 48 give rise to series 3 plus 6 plus 12 plus 24 plus 48 plus. Geometric series. When the terms of a geometric sequence are added, the result is geometric series. Another sequence 24, 16, 32 divided by 3, 64 divided by 9 leads to another geometric series 24 plus 16 plus 32 divided by 3 plus 64 divided by 9. Here the first term V1 equals 24. Common ratio R equals V2 divided by V1 equals 16 divided by 24 equals 2 divided by 3. Geometric series. Geometric series can be summed up using a formula. We will show you how to derive it. Let us define some of n terms as Sn. So Sn equals V1 plus V2 plus V3 plus V4 plus V5 plus V6. Vn, or Sn equals a plus a times r plus a times r squared plus a times r cubed plus a times r to the power of 4 plus a times r to the power of 5. A times r to the power of minus 1. Sigma underscore I equals 1, caret I equals n, AR caret I1 equals a plus a r plus plus and on to a times r to the power of n minus 1. To derive the geometric series formula, follow the steps. Sn equals a plus a times r squared plus a times r cubed plus a r to the power of 4 plus a times r to the power of 5. A times r to the power of n minus 1. Say, equation number 1. Multiply the sum by common ratio. R times Sn equals a plus a times r squared plus a times r cubed plus a times r to the power of 4 plus a times r to the power of n minus 1 plus a times r to the power of n. Subtract equation number 1 from equation number 2. Equation number 2. R times Sn equals a plus a times r squared plus a times r cubed plus, and so on. Minus equation number 1. Minus Sn equals minus a times r squared minus a times r cubed minus, and so to a minus a times r to the power of n minus 1. Therefore, r times Sn minus Sn equals a r to the power of n minus a. Most of the terms are cancelled following the subtraction, or Sn times r minus 1 equals a times r to the power of n minus 1. Or Sn times r1 equals a times r to the power of n minus 1. Sn equals a times r to the power of n minus 1 divided by r minus 1. If r less than 1, Sn equals a times 1 minus r to the power of n divided by 1 minus r. Problems of the geometric series. Problems of geometric series. Find the sum of 9 terms of the geometric series 2, 4, 8, 16, and on up to 9 terms. We start here from the first term. V1 equals 8 equals 2. The common ratio r is 4 divided by 2 is equal to 2, or 8 divided by 4 is equal to 2, or 16 divided by 8 is equal to 2. The sum of n terms formula of geometric series is Sn equals a times r to the power of n minus 1 divided by r minus 1. The sum of 9 terms is S9 equals 2 times 2 to the power of 9 minus 1 divided by 2 minus 1. As the first term V1 equals a equals 2, and common ratio r is equals 2, the sum of 9 terms are S9 equals 2 times 2 to the power of 9 minus 1 divided by 2 minus 1. S9 equals 2 times 2 to the power of 9 minus 1. S9 equals 2 times 512 minus 1. With simple calculations, S9 equals 1022. Problems of geometric series. Find the sum of 7 terms of the geometric series. 5 plus minus 15 plus 45 plus minus 135 plus up to 7 terms. Note the first term V1 equals a equals 5. Common ratio r is minus 15 fifths equals minus 3, or 45 divided by minus 15 equals minus 3. The sum of n terms formula of geometric series is Sn equals a times r to the power of n minus 1 divided by r minus 1. The sum of 7 terms is S7 equals 5 times 3 to the power of 7 minus 1 divided by minus 3 minus 1. Note here, the first term, V1 equals a equals 5, and common ratio r is equals minus 3. The sum of 7 term of the geometric series is S7 equals 5 times 3 to the power of 7 minus 1 divided by minus 3 minus 1, or S7 equals 5 times 3 to the power of 7 minus 1 divided by minus 4, or S7 equals 5 times 2,188 divided by 4. Equals 2 1,735. Problems of geometric series. Find the sum of 12 terms. Of the geometric series, 24 plus 18 plus 27 divided by 2 plus 81 divided by 8. Note the first term v1 equals 24. Common ratio r is 18 divided by 24 equals 3/4. Or r is equal to 27 halves times 18 equals 3/4 equals 0.75. The sum of n terms formula of geometric series when r is less than 1 is Sn equals a times 1 minus r to the power of n divided by 1 minus r. The sum of 12 terms is S12 equals 24 times 1 minus 0.75 to the power of 12 divided by 1 minus 0.75. The sum of 12 terms is S12 equals 24 times 1 minus 0.75 to the power of 12 divided by 1 minus 0.75. Or S12 equals 24 times 1 minus 0.75 to the power of 12 divided by 0.25. Or S12 is equal to 24 times 4, 1 minus 0.75 to the power of 12. Or S12 equals 96 times 1 minus 0.131676 and calculated as equals 92.95907. Problems of geometric series. The example. In a geometric series, second term equals minus 30, and the sum of the first two term is minus 15. Find the first term and the common ratio. Please note here, second term v2 equals ar equals minus 30. Therefore, f equals minus 30 divided by r. The sum of first two term is S2 equals a times r squared minus 1 divided by r minus 1 equals minus 15. Or a times r plus 1 r minus 1 / r minus 1 equals minus 15. Or a r plus 1 equals minus 15. Or minus 30 / r times r plus 1 equals minus 15 as a equals minus 30 / r. Or minus 30 times r plus 1 equals minus 15r. Minus 30 r minus 30 equals minus 15r. Therefore, r equals minus 2, as a equals minus 30 divided by r. Therefore, a equals 15. Problems of geometric series. A practical banking application. Example. A family decide to save money in an account that pays 9% annual compound interest calculated at the end of each year. They put $25,000 in the account at the beginning of each year. All interest is added to the account and no withdrawals are made. How much money will they have in the account on the day after they have done their 10th payment? Please note, this problem will form a geometric series with all payment as term and interest as common ratio. The first term B1 equals 25,000. The interest of 9% will be added to the amount after 1 year. After 1 year, when second payment is done, the amount will be equals 25,000 plus 25,000 times 9/100, or equals 25,000 times 1 plus 0.09, or equals 25,000 times 1.09. Or after 1 year, the amount will be equals 25,000 times 1.09. In beginning of the second year, added amount is 25,000. And total amount would be S2 equals 25,000 times 1.09 plus 25,000. After 2 years, the amount will be equals 25,000 times 1.09 plus 25,000 times 1.09. In beginning of the third year, added amount is 25,000, and total amount would be S3 equals 25,000 times 1.09 plus 25,000 times 1.09 plus 25,000. In beginning of the fourth year, added amount is 25,000, and total amount would be S4 equals 25,000 times 1.09 plus 25,000 times 1.09 plus 25,000 times 1.09 plus 25,000 equals 25,000 times 1.09 cubed plus 25,000 times 1.09 squared plus 25,000 times 1.09 plus 25,000 equals 25,000 times 1.295 plus 25,000 times 1.1881 plus 25,000 times 1.09 plus 25,000. Is calculated to equals 114,328.2. On comparing with a geometric series, S4 equals a r cubed plus a r squared plus a r plus a, where a equals 25,000 and r equals 1.09. If we use formula, S4 equals a times r to the power of 4 minus 1 divided by r minus 1 equals 25,000 times 1.09 to the power of 4 minus 1 divided by 1.09 minus 1 equals 25,000 times 1.09 to the power of 4 minus 1 divided by 0.09 is calculated to 114,328. And finally, after the deposit of 10th installment of 25,000, we apply series formula. S10 equals a times r to the power of 10 minus 1 divided by r minus 1 equals 25,000 times 1.09 to the power of 10 minus 1 divided by 1.09 minus 1 equals 25,000 times 2.367364 minus 1 divided by 0.09 is calculated to 379,823.2. This problem can be looked differently. The first installment will get interest for 9 years, and it becomes 25,000x 1.09 to the power of 9. The second installment will get interest for 8 years, and it becomes 25,000x 1.09 to the power of 8. And final, the deposit of 10th installment of 25,000 will get no interest. So the geometric series is 25,000x 1.09 to the power of 9 plus 25,000x 1.09 to the power of 8 plus, and on to plus 25,000. So sum S10 equals A times R to the power of 10 minus 1 divided by R minus 1 equals 25,000 times 1.09 to the power of 10 minus 1 divided by 1.09 minus 1 is calculated to 379,823.2. Another way to look into the problem: the last payment of 25,000 earns no interest, remains as 25,000. Previous payment earns interest of 9%, hence it is 25,000x 1.09. Previous to this payment earns interest of 2 years, hence it is 25,000x 1.09 squared. The payment of year before earns interest of 3 years, hence it is 25,000x 1.09 cubed. The process continue for all other years. And finally, the deposit of first installment of 25,000 earns maximum interest of 9 years. Hence, it is 25,000x 1.09 to the power of 9. So the geometric series is 25,000x 1.09 to the power of 9 plus 25,000x 1.09 to the power of 8 plus, and on to plus 25,000. S10 equals A times R to the power of 10 minus 1 divided by R minus 1 equals 25,000 times 1.09 to the power of 10 minus 1 divided by 1.09 minus 1 equals 25,000 times 2.367364 minus 1 divided by 0.09 is calculated to 379,823.2.
More practical problems of the geometric series. Now we take more practical problems of the geometric series.
A computer loses 30% of its value each year. Write a formula for the value of computer after n numbers of years. How many years will it be before the value of computer fall below 10% of its original value? Note here, the value of the computer will be down by 30%, or by a factor of 0.3 every year. Such problems, where each term will a factor of previous term, will result in a geometric progression or sequence and series. Let's start with original cost of the computer. Say A, and it will be first term of the geometric sequence. Therefore, first term B1 equals A. After 1 year, the value of the computer will be down by 30%. It means after 1 year the value of the computer will be equals A times 100 minus 30 divided by 100, or a 0.7. This is the second term. B2 equals A times 0.7. So, the common ratio R is 0.7. After 2 years, it will be 70% of AX 0.7, or AX 0.7 times 0.7 is equal to A 0.7 squared. This is third term B3 equals A times 0.7 squared. So, the value of the computers after n numbers of years will be n plus 1 term, or Vn plus 1 equals A times 0.7 to the power of n. How many years will it be before the value of computer fall below 10% of its original value? The value of the computer is less than 0.1 times A equals 0.7 to the power of n times A. Now check using a calculators. 0.7 to the power of 6 equals 0.1176, and 0.7 to the power of 7 is equal to 0.0823. It means after 7 years, it will be 8.23%, or below 10%. Problems of geometric series. A car originally worth 300,000 loses 15% of its value each year. Number 1. Write a geometrical sequence that gives the year-by-year value of the car. Number 2. Find the value of the car after 6 years. Number 3. After how many years the value of the car will fall below 100,000. A car originally worth 300,000 loses 15% of its value each year. Write a geometrical sequence that gives the year-by-year value of the car. If the car loses 15% of its value each year, the value of the car will fall to 85% of its value in the previous year. It means the common ratio is 0.85 fraction of 85%. First term, V1 equals 300,000, and common ratio, R equals 0.85. Using a formula of sequence, Vn equals A R to the power of n minus 1. Or Vn equals 300,000 times 0.85 to the power of n minus 1. A car originally worth 300,000 loses 15% of its value each year. Write a geometrical sequence that gives the year-by-year value of the car. Now find the value of the car after 6 years, as the first term V1 equals 300,000, and the common ratio R equals 0.85. Using a formula of sequence, Vn equals A R to the power of n minus 1. After 6 years, it means 7th term. V7 equals 300,000 times 0.85 to the power of 7 minus 1. Or V7 equals 300,000 times 0.37715 is equal to 113,144. A car originally worth 300,000 loses 15% of its value each year. Write a geometrical sequence that gives the year-by-year value of the car. Now tell us, after how many years, the value of the car will fall below 100,000? First term, V1 equals 300,000, and common ratio, R equals 0.85. Using a formula of sequence, Vn equals A R to the power of n minus 1. After 7 years, it means 8th term. V8 equals 300,000 times 0.85 to the power of 7. Or V8 equals 300,000 times 0.32058 is equal to 96,173. Therefore, after 7 years, the value of the car will fall below 100,000. Problems of geometric series. Number of people in a small country town increases by 2% every year if the population of the start of 1990 was 12,500. What is the predicted population at the start of 2030? Number of people in a small country town increases by 2% every year if the population of the start of 1990 was 12,500. What is the predicted population at the start of 2030? Since the quantity is increased by 2%, so multiplying factor will be 100 plus 2 divided by 100 is equal to 1.02. Or the common ratio of geometric progression, R is 1.02. First term, V1 equals A is 12,500. The second term, that is in 1991, will be V2 equals 12,500 times 1.02. Third term, that is in 1992, will be V3 equals 12,500 times 1.02 squared. In 1993, the fourth term, V4 equals 12,500 times 1.02 cubed. The common ratio of geometric progression R is 1.02. First term, in 1990, V1 equals A is 12,500. The population at the start of 2000 will be the 11th term, and at the start of 2030 will be 41st. So V41 equals 12,500 times 1.02 to the power of 40. The calculation may be done by calculator or by log table. V41 equals 12,500 times 1.02 to the power of 40 is equal to 12,500 times 2.208. Predicted population at the start of 2030 will be 27,600. Problems of geometric series. A bank account offers 9% interest compounded annually if 7,500 is invested in this account. Find the amount in the account at the end of 12 years. Since the amount is increased by 9%, so multiplying factor will be 1.09, or the common ratio of geometric progression, R is 1.09. First term in start. V1 equals A is 7,500. The second term, after 1 year, will be V2 equals 7,500 by 1.09. Third term, after 2 years, V3 equals 7,500 times 1.09 to the power of 2. Therefore, after 12 years, V13 equals 7,500 times 1.09 to the power of 12, calculated to 21,095. Problems of geometric series. When a ball is dropped onto the floor, it bounced to 65% of its height from which it was dropped. If the ball is dropped from 80 centimeters, find the height after fifth bounce of the bounces. Watch. When a ball is dropped onto the floor, After the bounce, the ball loses its height to 65%, so multiplying factor will be 0.65. Each bounce will make a geometric sequence. The common ratio of R is 0.65. First term, in start the height, V1 equals I is 80 centimeters. After the first bounce, second term will be V2 equals 80 times 0.65 is equal to 52 centimeters. First term V1 equals is 80, and the common ration R is 0.65. After the second bounce, third term will be V3 equals 80 times 0.65 squared. After the third bounce, fourth term will be V4 equals 80 times 0.65 cubed. After the fourth bounce, fifth term will be V5 equals 80 times 0.65 to the power of 4. After the fifth bounce, sixth term will be V6 equals 80 times 0.65 to the power of 5. Therefore, V6 equals 80 times 0.116 is equal to 9.3 centimeters. The final height after the fifth bounces is 9.3 centimeters. Thank you very much for watching the videos. Please continue to watch our videos and subscribe to the channel.